Okay, so we are right now between the last couple of classes of electronics and signals. We've been talking about and talking around the concept of feedback. We use feedback in electronics for our last topic or previous topic to this, which was oscillator circuits. And in that particular case, we used positive feedback to make the circuits oscillate. Right, we spoke about, and we've actually have come across the concept of negative feedback about 5 or 6 times now. And just as an aside, we took a systems approach to this in another course. Those of you who are doing it, to show how you can represent at a systems level a block diagram with feedback and how you simplify it and so on. So today, we're going to introduce, just look at some of the concepts in an introduction to feedback amplifiers today, and we'll complete it tomorrow. And it is not, these particular topics or this particular topic is not so much about circuit design, but about the concept on a system-wide or a system look from the electronics perspective, right? So the actual nitty-gritty of how you design the type of amplifiers that we're going to talk about, that is a lot more complicated. And in fact, you can do a whole course on that kind of circuit design. We're not dealing with that here. At this level, it's just to look at the concepts related to feedback in amplifiers and some of the benefits of using negative feedback in the various types of amplifiers that we will encounter. All right. So this again, part revision again, and part reinforcement of what we've done before. A feedback amplifier is one where you have a portion of the output fed back into the system and combined with the input. And this is a kind of block diagram. We've used this block diagram. We've used various symbols around the place. This particular one is negative feedback. We met that before. And again, just from what we've been doing, if the amplifier had a transfer function of G and the feedback network had a transfer function of H, of course, the S's are understood. The overall input-output relationship was G over 1 GH. And the sign here, was the sign a plus or a minus? Is negative feedback, so what sign is going to go inside of here?
Plus.
A plus, right? So negative feedback, so if you have a block diagram of this nature for, in this case, an amplifier that happens to have feedback, the overall transfer function, in other words, output over input, is going to be G divided by 1 plus GH. These are the kind of, these would be the circuits that are composed of operational amplifiers, transistors, field effect transistors, and the like. And the feedback network would be, again, it could be transistors or it could be just a passive network composed of resistors and so on. The amplifier, so again, what you may feedback for the amplifier, you may feedback either voltage or current. Right, so from the output of the amplifier, we can either take the output of the amplifier, maybe voltage or current, and we will see the types just now. So if that is the case, we can feedback voltage or current into the network, and then we can combine either the voltage or current with a type of input, right? So in the general form, the sort of black box, if you like, the input to these amplifiers could be voltage or current. The output could be voltage or current, and the feedback, of course, will be voltage or current as required. And in terms of some of the terminology used, an amplifier where the feedback circuit is a series circuit. In other words, this feedback now is sending back a signal, sorry, and the summing junction is a series circuit. It means that we are mixing in that the input is voltage and we are mixing it with our feedback voltage. All right. If you're dealing with a shunt circuit, then it means that the input is current and you're feeding back current. Right. So anytime you see the terminology, we're going to meet this around the time. Anytime you see something revolving around series, typically you're talking about something with voltage. And anytime you see something related to shunt meaning in parallel, you're dealing with current or feedback current. And usually this is just a simple resistor network. It may be more complicated, but at this point in time, we are treating them as boxes. There's an amplifier block and there's a feedback network block, okay? So there are many benefits of feedback. We're not discussing this just for the sake of it. We have seen elsewhere that feedback does some things. So if you have positive feedback in a circuit, you're able to create with op-amps, you can create oscillators. We've spoken about the concept of negative feedback already when we spoke about like the power supply regulator, where what the feedback is trying to do is to, if there's a drift in something, usually the output, the feedback acts in a way, the negative feedback acts in a way to reduce the output drift and to get you back on course. So the benefits in terms of an amplifier, if you have an amplifier, which is a circuit to take a small signal in, which may be voltage or current, and give you a large either voltage or current coming out, some of the benefits is that one, feedback increases input impedance. You remember, if you have a circuit and you have a source, and this is some circuit, what you want to increase the input impedance here. You want to increase that because by increasing the input impedance, the majority of the source, the signal from the source, develops across the input to the circuit. If the impedance is low, then what happens is that the majority of the signal tends to remain in the source and very little gets passed. And you could think of it like a resistor network. Right? If you have two resistors, R1 and R2, and I have some voltage here, right? If R1 is large compared to if R2 is large compared to R1, most of Vn appears across R2. But if R2 is small compared to what's R1, most of Vn appears around R1. And if you're taking this signal, if this is where you want the useful signal to be propagated, if R2 is too small, you get a very small signal. And in fact, what you do is load the source. The source is dropping all of its signal inside instead of on the load itself. All right, everybody seeing that? Make some sense? Yeah, no? Right. So on the other side now, you want to lower the output impedance for the same thing. Remember, the output impedance now is that you have inside the amplifier, your circuit, and you want to supply a load. So if this is a load, you want to make the internal impedance of this circuit as low as possible so that most of the output appears across the load. So in other words, ideally what you want is a high input impedance and low output impedance. Then we spoke about this already, that components tend to drift. When transistors get warm, when circuits heat up, when they start to carry current, the actual values that you design them with may change. And if that is the case, things like an amplifier, you may find the gain tending to vary from what it should be or what it was designed to be to something that is maybe undesired. An oscillator was a case in point, that you have a particular oscillator like the Weinberg oscillator. If you recall the Weinberg oscillator, the amplifier have to have a gain of 3. If you design it for 3, but as the oscillator starts to drift, the gain goes up to 3.1, it stops oscillating. Or if it goes down to 2.9, it stops oscillating. So we do some things and adjust. This is just one application, but we do some things to make to stabilize the gain. In some cases, it's more important than others. And as we will see, and we will prove it, one of the things that you do, unfortunately, is that by varying the gain, you kind of low, you reduce the overall gain of the device, but it at least stabilizes it. So you have to design accordingly, and we'll talk about that. You improve the frequency response of it. A lot of you all may recall something called the gain bandwidth product for amplifiers or op amps. One of the things that feedback does is that gives you it increases the frequency response of the amplifier. And then just in a general term, we're not going to talk too much about it, but you get things like improved linearity. Remember all the way through we've been talking about linear systems. So it makes it linear or improves the linearity of it. And then we tend to lower distortion and noise. Okay, not going to spend much time about this, but this is specifically electronic noise, thermal noise, and the like that you would have met maybe in level 1, or you may have come across some of it in your high school physics as well, when you were talking about when you first met semiconductors. Okay, so amplifiers, as it turns out, there isn't one type of amplifier. There are in fact 4 of them, depending on what the input is and what the output is. There are voltage amplifiers, current amplifiers, transconductance amplifiers, and transresistance amplifiers. All of them exist, and they're all circuits that can be made or bought to perform these functions. So we're going to look at them and then use some equivalent circuits as well to derive some simple expressions for the input and output relationship for them. The first thing is the voltage amplifier. This is the one that you've been meeting a lot, right? You've met this in a simple things like an op amp. You set it up, you put a small voltage in, and you get a larger one coming out. So the voltage amplifier accepts voltage at its input and delivers a voltage at its output. So if you want to sort of model the equivalent circuit of it, what we use is, and you remember these things from your introduction to electrical engineering in year 1 and introduction to circuits and so on, is that once you're dealing with voltage sources, remember the voltage amplifier is taking a voltage in and generating a voltage out. We use a Thevenin equivalent circuit. And what the Thevenin circuit means is that you can replace all of the various voltage sources and signals coming into the amplifier as a source in series with a resistance, and this is the input of the amplifier. The amplifier is producing voltage coming out, so all of the circuitry in the amplifier itself we can replace as again a voltage source in series with an output impedance that is now feeding the real world. Okay, and we know that in the case of the voltage amplifier, this is my signal coming in and this is my signal source impedance. What we want is that the input impedance of the amplifier is high, so most of this signal appears across as Vin. The amplifier has a voltage gain that we know. So inside all of this fancy circuitry of the amplifier, it takes Vin and gives you AV times Vin as the amplified voltage. And it feeds this out to the real world through some impedance that hopefully is going to be very low. So this is this sort of Thevenin source for the output. And here you have the real world, and the relationship between the input and output is a V out, right, which is supposed to be appearing here, is the voltage gain of the circuit by V in, which is appearing here. Ideally, R in, which is the input impedance for the amplifier, is supposed to be huge, close to infinity, right? So that Vs essentially appears as Vn, right? And then all of the signal that is generated by the amplifier is supposed to be dumped across the load so that the output impedance actually is supposed to be low, ideally 0. Make sense? Yeah? We've spoken about this in some various forms already. All right? The next one, of course, is a current amplifier. A current amplifier takes a current in and delivers a current going out. Current circuits we model as something called a Norton equivalent, which is a current source in parallel with a source resistance. So what happens here is that, remember, you want the majority of the current to be going into the amplifier. So a current amplifier is supposed to have a low input impedance. The sources, whatever the sources are here, is modeled as a current source in parallel with an impedance that is supposed to be very high. So that when this is in parallel with the input impedance of the amplifier, most of the current is going to go into your amplifier. If it is a current amplifier, it has a current gain. So that the amplifier, the output here, right, is AI, which is the current gain, times whatever input current appeared. And again, because it's a current source, we model it as an ideal source in parallel with a very high resistance or impedance, and most of the current is delivered to your load. Okay, so ideally, what you want here, now this bit is inside of the amplifier, remember. So ideally, what you want is that the current amplifier has a very low input impedance and a very high output impedance, which is the opposite of the voltage amplifier. Right? Low input impedance, so all of the source current comes in. High output impedance, so that all of this, the current that is amplified, goes out. All right? And of course, the relationship is output current is equal to input current times the current gain. Then we have these, the next two that we're going to meet. There's one called a transconductance amplifier, which takes voltage in and gives you current coming out. So there's a voltage somewhere, and the amplifier takes that voltage in. The circuitry converts that voltage to a current, amplifies it, and then provides a high current coming out. So that this one now is a hybrid. Because we're taking a voltage in, all of the voltage side of the input, we have to use a Thevenin equivalent, which is a source in series with an impedance. And because it's a voltage source, the input impedance here has to be high, ideally close to infinity. Just sort of, I saw a question here. Okay, I'll come back to that in a little while, Krista. Right? So you want the voltage high coming in. Sorry, you want the impedance high coming in, so that most of the impedance, most of the voltage is dropped across Ri. It's a device that is taking voltage and converting it to a current. So it's inside of the amplifier, the output part of the amplifier is a current source. And if it's a current source, the Norton equivalent current source will be a source in parallel with a very high output impedance. So in other words, the transconductance amplifier has a high input impedance, so you don't load the voltage, and a high the signal, and a high output impedance, so that most of the current heads out of the circuit. Right, back to that question. Why would you want the opposite for the current amplifier? Low input impedance and high output. Right, back to that. Remember what a current amplifier is doing, right? If this signal source is current coming in. So if you have current coming in and the signal has a source impedance, all sources have some impedance associated with them. What you want is a majority of the signal current to head into the amplifier. This is the useful bit here. This is useful. this bit tied to the current source, whatever the signal happens to be, this is not wanted. So ideally, you want this to be 0 and you want this to be 100%, because this is what you need. So the only way you could have that is if the input impedance here is very low. If this is very low compared to this, then most of the current is a current circuit coming in here, is dividing between these 2 points, the internal source of the internal impedance of the source and the internal impedance of the amplifier going in. If this is much lower than this, all of the current going to head this way. The closer this gets to 0, the more current heads in. So you want a low input impedance. Make sense?
Yes, sir.
All right. And similarly, when you're heading on the other side, you're generating current. So the circuit inside of the amplifier is producing current. You want all of that current to head out. So in other words, you don't want any to be lost in any internal impedance of the amplifier. You want all of it to be sent out towards the load. So if this is also high here, if this is high, then hardly any current is going to be retained inside of the circuit. All is going to head towards the load. Okay, and high and low, of course, are all relative, right? Remember, nothing is ever 0 or infinity kind of thing. But what you're looking for, and this is why I said the actual circuit design is a lot more complex. We're just looking at it from a block diagram and understanding what the concepts are. But a lot of this depends on what this is. So if this is 600 ohms for the load, RO has to be typically, maybe 100 to 1,000 times more than that for you to have a high output impedance relative to the load. If this is 8 ohms, like a power amplifier case for audio, RO may only have to be maybe 100 times or 1,000 times as big. It's all relative. And that design is very circuit specific, which is not what we are about. Okay? And we saw the transconductance voltage in, current out. And we'll see where we use that in a couple of seconds. And this one needs high inputs and high output impedances. And then the trans resistance or trans impedance, they use the both terminologies. In this case, again, is taking a current in, which means that the current side here, you have to model as a Norton equivalent, a current source and a high input impedance, so that if the input impedance for the amplifier is low, most of the source current goes in to the amplifier because we need that. The amplifier is taking that current in and generating a voltage out. In other words, it's amplifying, converting the current to voltage and giving us a high voltage relay in relation to the current. So the voltage source output now is going to be a Thevenin, which is a voltage and an impedance. This has to be low so that all of the voltage drops across your load. Okay, and just let me back up a little bit. The input-output relationship for a transconductance amplifier, output current, you put V in, and it generates a current related to that, and we call that particular gain the transconductance of the amplifier, the transconductance or the transconductance gain, some people call it, and typically they use the symbol G for it, right? So voltage gain is A subscript V, current gain is A subscript I, transconductance is capital G. In some cases you have a subscript M associated with, some textbooks use it. And then the trans resistance amplifier, you're putting current in and you're getting voltage coming out. And of course, the input-output relationship is something called the trans resistance of the device, and they use a capital subscript M for it. Okay? So if you were to summarize all of them in a table, this is ideally what the four amplifier, the characteristics look like. The voltage amplifier, the current, the transconductance, and the trans resistance. The transfer functions were the ones that we have been seeing this all the time. The V out is voltage gain by voltage in. The current amplifier, current out is equal to current in by a current gain. The transconductance, you're sending current and you're getting voltage out. The transresistance, sorry, you're sending voltage and you get current out. The transresistance amplifier, you're sending current and you get the voltage coming out. And these are the sort of characteristics that we want, that we just all summarize here. In terms of the input impedances, the voltage amplifier has to have a high input impedance, low output. The current is the opposite. The transconductance, because it's current in and current out, you want high input and output impedances. And the transresistance, low input impedance because it's a current in, low output impedance because it's a current out. All ideal, right? So these normally, when you're talking about input impedances, you're talking about the megohm range here, right? And 0 here, you're talking about typically less than 10 ohms. And in some cases, a lot less than that, okay? That is like the sort of levels that you may get, even lower than that. Okay, so everyone following so far, the concepts behind them, right? And you've met some of these, so let me show you just for you to realize that we actually encountered this without, at least 2 of them without realizing it already. You know from level 1, the common emitter voltage amplifier, or a non-inverting voltage amplifier, or inverting voltage amplifier. There's voltage in and voltage out in both cases, right? In this case, this is the discrete transistor version. So you put a voltage here, a voltage signal here, you get a voltage coming out. Same thing for this one. If it's inverting, then it's just flipped around by 180 degrees. The current amplifier, in fact, we met when you did the regulated power supply. The pass transistor in the regulated power supply is in fact operating as a current amplifier. Remember, the power supply is designed to give a load current, a voltage at a particular load current. But that current you supply from the base of the transistor, the pass transistor. And the HFE characteristic of the amplifier takes the base current and gives you the collector current. So this, in fact, is the AI, if you want, the current gain, right? And in fact, that is what HFE is when you would have done it, right? Sometimes we can't provide enough current gain with one transistor, so that's when we hook up another transistor to it, and that's when we came up with the Darlington pair, right? So the regulated power supply, the output stage of the regulated power supply is in fact a current amplifier, right? So you met that already. This we haven't met, but it's used all over the place. The transconductance amplifier is something known also as a voltage controlled current source. Where they use these is a voltage to current converter, and they use these a lot in the process industry, in the control sector. You remember us talking about how do you get signals, for instance, like a temperature signal from somewhere across a plant, a half a kilometer away from the control room. There are a number of ways to do it, but one of the ways that they use is something called current signaling. And they use a current, it's governed by a standard, right? There are documented standards from like the Instrumentation Society of America, and you're going to meet that in ECNG 2009. So everybody, standards make sure everybody do the same thing. So my equipment could communicate with your equipment and so on. There's a standard for current signaling using something called a 4 to 20 milliamp loop. So what you have is, if you have something, let's say a temperature, and you have a control room here, this is the room with a control room. You get the signal, the temperature, whatever it is, a thermocouple, a thermistor, whatever it is, has something, so it generates, let's say, a voltage. That voltage is converted to a current and sent along a line to the control room. And the current is between the range of 4 to 20 milliamps, meaning 4, meaning you have the lowest end, 20 milliamps, meaning so 4 will correspond to, let's say, 0%, 20 milliamps will correspond to 100%. Right? So you send it along a wire because once it's a current source, you're sending this, so it will push this regardless of what the impedance of that piece of wire is. So you send that and it's voltage in, current coming out. So it's a voltage to current converter. This is a block diagram of a particular version of this. Is something called an operational transconductance amplifier. That's what OTA stands for. So this is just a block diagram and of it. These are the manufacturers. So this is a type of device that exists. And the input output, you get an input voltage. This is the transconductance. They're using a small g, or you could use capitals, and it's producing a current somewhere in the 4 to 20 milliamp range relating to the current. Any idea why they don't, why they want to start at 4, not say 0 to 20, use 0 milliamps to 20 milliamps, so 0 being 0% and 20 milliamps being 100? From what you know about engineering, why would I not use 0 to be 0? In other words. Any takes on it? Anybody? Okay, somebody say you won't get exact 0, which is, oh, that's a point. Induced currents, meaning what? Meaning what, Joshua? When you say induced currents? Okay, let me give you a, what happens if, okay, if I'm sending a current here and the wire breaks, what happens to the current? The control room sees what? If you're sending some current, whatever the value is, right, the control room sees 0. So in other words, if I have 0 as 0%, I really don't know if there's a broken wire with 0, or if the system is actually sending 0 amps. So in other words, you need to use something to signal in such a way that you could also detect 0 when nothing is happening. Right? So that's the answer, yes, Krista. So what they did is that 4 to 20 is an odd number, and that has some historical things. When you're doing controls, you'll see why they actually selected that, but they don't use 0. So if you do get 0, then somebody knows that the wire, the communication line between the temperature sensor, whatever the sensor is, and the control room is at fault. Right? Once it's operating, you're going to get somewhere between 4 and 20. If you get less than 4 or down to 0, then something isn't working. All right? And then at the other end, if you're sending what do you call it? Voltage to current, at the other end, you need something to convert the current back to a voltage. And that's where the transresistance amplifier comes in. So there's a sort of an opposite side to this, which is the transresistance amplifier or the transimpedance amplifier, that takes the current now and converts it back to a voltage. All right. There are also other types of transimpedance amplifiers. For instance, a photodetector. A photodetector for a photodiode. The photodiode would produce current, and that is converted to an output voltage. All right. And there are other types of sensors that work with that. And just by the way, what's the simplest current to voltage converter you could have? What is the simplest current to voltage converter? The simplest current to voltage converter is one of these, a resistor. A resistor takes current and it develops a voltage across it, right? So if you want to detect a current, one way is to just simply put a resistor in series with the current. So the current passes through the resistor and it develops a voltage, right? Of course, the resistor has to be very small so they don't affect the value of the resistor, but the current itself by blocking too much of it. But a very simple voltage to current converter is a resistor, but of course it doesn't amplify. Okay, so the transimpedance amplifier behaves like a resistor with gain. Yeah. Right. So let's look at a little bit for the rest of the class as to how the feedback works. So you have an amplifier. I'll just pick one at random. So we have a transresistance amplifier, current in, voltage out, and I want to apply feedback. So in other words, this particular amplifier, I now have to take output, pass it through some network, and feed it back to the input. Right? Remember, this is open loop. So this is like the block diagram. All we have is this so far. Right? This is either the voltage, the current, the transimpedance, or the transconductance amplifier here. So I'm now going to have to take something on the output and supply it back to the input, negative feedback, right? So input here, output. If I'm taking here, I have a little transfer function here, my feedback network. So there are two things inside of here that, remember, the input could be voltage or current, the output could be voltage or current. All right, and we saw the four combinations here. So when I'm feeding it back now, I could feed back either voltage or current. Sorry, I can sense either voltage or current at the output. And I can feed back from here either voltage or current depending on what the input is. So again, we have four combinations to deal with. Everybody seeing that? The input could be voltage or current, the output could be voltage or current. And we have four combinations of that. So depending on what I have to feed back, I could be sensing either voltage or current and feeding back either voltage or current, depending on what the configuration of this is. Fair enough? Let me know. Right? So here are the combinations now. If the voltage amplifier, you are, look at how the terminology here, the voltage amplifier uses, and we have a two-part name here, voltage series feedback. The first part of the name is telling you what I am sensing. In other words, this is the output. So a voltage amplifier has voltage at the output. So in other words, the parameter that is being sensed on the output is voltage. I have to feed back voltage. If it's a voltage amplifier, it means V out and V in. So I have to feed back voltage. The only way to feed back voltage is in series with another voltage. Right? So, and we'll draw the circuits in a second. So a voltage amplifier senses voltage and feeds back voltage. The voltage happens to be in series. So this is like voltage feedback, if you like. The transresistance amplifier, which is the other amplifier that has voltage at the output, sends current back. So this is voltage at the output, and I have to feed back current because the input part of the amplifier is a trans resistance, right? The output, if you look at the trans resistance here, right? The trans resistance output is voltage, but output is voltage, but input is current. So in other words, for a trans resistance amplifier, I have to sense voltage coming out, but I have to feed back current. All right? Current feedback is also called shunt feedback. All right? The transconductance amplifier is the opposite. The output of the transconductance amplifier is current, so I have to sense that. The input of the transconductance amplifier is voltage, so I have to feed back a voltage. So this is current, and I'm feeding back voltage. Voltage, like here, has to go back in series, and the current amplifier is current output, current input, so the input current has to come back in shunt mode, and you'll see why in a second. All right? So just the terminology is there. When you see the two-part name, the first part is telling you what the output is, right? And you know it, of course, from the type of amplifier. The second part of the name is related to how you have to feed, what the parameter is and how you have to feed it back, okay? So let's look at the first one, the voltage amplifier. Voltage series feedback. It's a voltage amplifier. So if this is the voltage amplifier here, you remember the voltage amplifier is a Thevenin equivalent device, right? Thevenin equivalent model, sorry. So you're generating voltage at the output. So if I have to feed back voltage, it's V in and V out, I have to sense the voltage. So I have to sense the voltage across the load. The feedback network has to feed back voltage, but it's negative feedback. So in other words, the feedback polarity has to be this way, minus plus. So notice that this is subtracting Vs is equal to this. If you like, V in is equal to Vs minus this voltage now. Everybody seeing that? Yeah, no, maybe? Make sure. Right. So the voltage amplifier, which is the most common one, the most familiar one, voltage on the output. So we have to sense the voltage across the output, and we have to feed the voltage back in series with the input voltage so that we get the negative feedback here. And of course, the relationship here, beta, right, is VF. You have V out here, and you have VF coming back here, right? VF is beta times V out, right? So it's a part of V out coming back, right? And we've seen we could do this, for instance, with a simple resistor network. If this is V out, we could take VF like that, okay? We've seen that kind of behavior already. The transresistance amplifier, that's the other one that has a voltage coming out. Notice again, you have to sense the voltage. So you have to sense V out coming. But this now, the transresistance amplifier has current coming in. Remember, the current is a current source, a Norton equivalent. So to get feedback, if this is the source current coming in here, to get negative feedback, some of that, you have to reduce what is going in by your feedback. In other words, IS is equal to I in plus IF, so that the actual input I in is equal to IS minus IF, right? So that's a negative feedback right here. So you connect it, and this is how the shunt feedback, notice that it's connected in parallel with the source. That's why it's called shunt. If you were in series with this source, this is what series is. This is in series with the source. right? This is in shunt with the source because you have the shunt current and the feedback current in parallel. In other words, the source current is splitting into two. You can look at it that way. Part of the source current, some has to go to the amplifier, and some has to go to back to the feedback network. And again, the relationship is V out and IF coming this way. Yeah? So voltage, shunt. Current, series feedback. This is a transconductance amplifier. So it's voltage in, current out. So if I have to sense the current, it means that I have to put my input network in series with the output, so that the output current passes through the network, right? It has to become part of the network. This network, become part of the output. This network takes that current and produces a voltage. As we said, the simplest way you could do that is a resistor, right? So I could put, for instance, if I were to, this is my output here, right? If I put a resistor here, this resistor is now providing the current sensing, and I have a circuit inside of here that amplifies that voltage and will give me a voltage coming out, right? Series, because it's a voltage coming out, it has to go in series with the input and of course provide negative feedback. So again, Vs is equal to Vf plus Vin, or Vin is equal to Vs minus Vf, your negative feedback. And the last one is the current shunt feedback. So you're sensing current, again, in this case, so you can sense the current the same way, like with a resistor, but this circuit is taking the current and providing some fraction of the current. There's an input-output relationship, current in, current out. So this could be like a pass transistor kind of arrangement. So the current that is sensing is going into the base of a transistor, and the collector or the emitter of the transistor is supplying the current coming out, and beta will be the HFE arrangement. Because it's current, and because the current source is modeled as a Norton, which is a source in parallel, you have to have, again, that the feedback has to be in parallel with it, such that the Is is equal to IF plus In. Therefore, In is equal to Is minus If. Again, your negative feedback. Yeah? Everybody following the arrangement? When you get it, you have to go over it a couple of times just to make sure you understand it. Sketch it, draw it, make sure you understand. When you're dealing with voltage coming back, that's a series type feedback. When you're talking about current coming back, that's a shunt type feedback. In other words, it's in parallel. Yeah? And then we remember this from before, that the feedback calculation, remember, generic, that if the feed forward group was A and the feedback network was beta, we derived this last time and we also derived it elsewhere, that the whole transfer function is A over 1 plus A beta, because we're dealing with negative feedback, that's positive here. Right? We also spoke about that the quantity A beta is called a loop gain. And we saw that in the case of oscillators, right, we wanted A beta to be 1 so that the thing would oscillate. All right. What absolutely has to happen, of course, is that the assumption always is that the signal goes from input to output through A, and that the feedback goes from the output to the input through beta. Never does the output go back through A, or never does the input go to the output through beta, right? That is the way this thing has to work. So whatever it is, and this is why I said that the actual circuit design, we're just dealing with the requirements here. but the actual circuit design is a lot more complicated. We're just dealing with the concepts here, right? This, I will talk about this tomorrow, just as about if we convert it to decibels, right? But this is just what I was saying, that the feedback, the input signal must go through A and not beta. Feedback must go through beta and not A, all right? And that the whatever beta is has to be independent of the load and source resistance. In other words, beta does not depend on what is happening here or here, the output. Okay? So those are the concepts. It's a different, what shall I say? So some different topics in a way. We covered some of them without knowing it before, but we try to put a name to some of what we've met before, the particular types of amplifiers. So your takeaway here is that there are 4 types of amplifiers, right? And for the 4 types of amplifiers, depending on whether you're amplifying voltage or current, and whether the input and output is a voltage or a current, there are also 4 ways that you could supply negative feedback to that. And the 4 ways, again, depend on if you're sensing voltage or current and you're feeding back voltage or current. If you're sensing voltage or voltage, then the type of feedback is going to be voltage something feedback. If you're feeding back voltage, it's series. If you're feeding back current, it's shunt feedback, because the current has to feed back in parallel with the input. Okay? All right? So any questions? You have to review this thing again, and tomorrow we're going to see, we said that the feedback provides, let me show you some right here, that feedback produces some of these positive effects for us. So tomorrow we're going to look at actually see now, using that same formula of G over 1 plus GH, how when you put feedback into one of these amplifiers, how it either increases the input impedance or lowers the output impedance and so on. Right, so you'll do a little bit of analysis with that. There's no circuit theory in here. This is all like a systems approach to it. And we will take it from there tomorrow. All right, and in the second half of the class, we will have a we look at problem set 2. Right, so at least look at the problem sets and so on. I'll organize the solutions for you. But I'm more interested again in your approach to it. Most of the answers are in the slides anyway. In notes, it was sort of designed that way, and you have to do a couple of calculations as well. All right. So if there are no major questions at this point, or think about it and sort of hit me with the questions tomorrow when we meet in class face to face, we can run over any of this and very easily, and then go forward with the rest of the concepts. Right? Okay. All right. So let me stop the recording here.